do another example. Let's do a square root function. Let's look at problem 2 and see what we have in this one. In problem 2, we're looking at a parent function. All right, so I'm going to go ahead and talk about our parent model. So we'll put that here beside it. When I see problem 2, the first thing I'm thinking is y equals x squared x. Right? All square root functions, right, come from the graph of y equals the square root of x. So if you want, let's build a quick sketch of the square root of x function. So just to show you square root of x, well, you could build a table of points, right, if you wanted to apply the translations. But I know that, for example, square root of 0 is 0. I know the square root function. It begins here at 0, 0. I know domain of all even roots, like square root of x, 4th root of x, 6th root of x. We've got to have x being greater than or equal to 0 because you can't take the even root of a negative. So you'll notice the domain, all these x values, all these points take place at 0 or any positive number. So take place on the positive side of the right axis, including 0. Now, for example, we could let x be 1. We all know the square root of 1 is 1. 1 1's on that graph. We could let x be 4. What's the square root of 4? Square root of 4 is 2. Right? So right now, if you're looking at the graph of our square root function, here's y equals square root of x. That's the parent function. Now, what I want to do is graph f of x. So we're going to talk about the changes that take place. And I'll circle them. There's 3 transformations in this problem. I've highlighted them right here. So the first thing I'm going to do, all right, is I'm going to talk about this negative inside here. What does this do? Let's list the transformations. So the negative, right, inside here, that causes my graph to reflect. So we're going to reflect the graph, right, of y equals square root of x, which we already have graphed over here to the side. We're going to reflect it about the y-axis. Anytime you multiply your domain variable x by a negative, it's going to flip your graph across the y-axis. It's going to take every ordered pair, and I'll write that down. All right, let's put it up here. Every ordered pair, every point x, y, you will find the ordered pair negative x, y on your graph. So for example, 1, 1, if we reflect across the y-axis, we would be at negative 1, 1. 4, 2, we reflect across the y-axis, we would be at negative 4, 2. So right now, this would be our graph. I'll dash it in just to show you again a sketch. There's y equal to square root of negative x. That takes care of the negative. It flips it across the y-axis. It multiplies every x coordinate by a negative. So you can see that translation. All right, now that takes care of that negative. Now I want to look at this 2. What does that do to my graph? Well, when you multiply your function by a constant, you're going to be stretching or shrinking, or sometimes referred to as compressing, your graph vertically by the y-axis. So a stretch or a compression comes into play vertically. Now, with this number being greater than 1, right, we have a coefficient of 2 here. This implies we're going to have a vertical stretch. So let's write it down, our transformation. Vertical stretch by a factor of 2. All right? Well, let's go ahead and take that. So if we stretch this graph vertically by a factor of 2, all right, I'm going to go ahead and show that. So as we're looking at our points right now, negative 1, 1, right? Negative 1, 1. We would multiply each y coordinate by 2. 1 times 1 is 2. So it would move to negative 1, 2, right? Negative 4, 2. We multiply the y coordinate by 2. We would move up here to negative 4, 4. Right? So I'm going to plot a couple of these points. Negative 4, 4. Right? Negative 1, 2. 0, 0, of course, multiplying the y coordinate by 2 wouldn't change anything. But just showing you here in red. Right, here's our graph. This will be the graph of y equal to 2, right? Square roots of negative x. So there's the stretch vertically. And now we have one last change to take place. And let's look at it. So let's go ahead and talk about this -3 on the outside. All right, and we'll go down here and write down the effect of it. Now, subtracting a 3 from the function, mentioned this in our last example, causes a vertical shift down 3. So plus we go up, minus we go down. We're adding or subtracting a constant outside the function. Shift down 3 units. So if we were to finish off our graph, this point 0, 0, if we go down 3 units, let's shift all these points down. We're going to subtract 3 from every y coordinate. So we're going to be beginning now here at the point 0, -3. All right, where's that point -1, 2 move? Well, take the y coordinate, subtract 3 from it. What's 2 minus 3? -1. So that -1, 2 point is going to move down here to -1, -1, right? So we could plot that point, -1, -1. Where's -4, 4 move to? Well, so we subtract 4, or we subtract 3 from 4, we get 1. So move down here to -4, 1. So we'll go ahead and plot that point right here at -4, 1. All right. Now our graph, and we'll go ahead and put it here again in this green color. All right. You can see our graph shifted down. Again, we'll plot that point here, -4, 1. But there's my graph of my function. So there's f of x. So you can see I stepped it off step by step. F of x. So there's our function. F of x equal to 2 square roots of -x minus 3. All right, just walking off the transformation. So that one had the vertical stretch and reflection property introduced into that one. All right. So again, that's reviewing transformations. A couple examples. We'll take a break and we'll continue on and look at some more. All right. But this is getting into transformation properties.